Hey guys, today we're going to look at the general form of the exponential function in word problems. So first let's start off. It says the general form of exponential functions is y equals a times b to the x, where a, this is our initial value, b is going to be our growth or decay rate. X is going to be our time. Sometimes that's measured in days, years, months, just depending on the problem. And Y is going to be whatever our total is that we're looking for. Okay, so as we look at this next part here, we're going to find out, is the table given a growth or decay function? So it says, for each of the following, let's determine the growth or decay factor. Okay, so that's a little bit different, this factor piece. Okay, and then we're going to state if we have an exponential growth or decay function. So the factor is going to be that number that we multiply by every single time. So when we're looking at example 1 here, I'm asking, how am I going to go from 6 to 12? How am I going to go from 12 to 24 and 24 to 48? And sometimes in this case, it's very easy to see that every single time we're multiplying by 2 here. So this growth or decay factor is going to be 2. So in our problem, that would be our b value from our equation. So based on that b value, which is greater than 1, we know that this is an exponential growth problem. But number 2 is not as easy to see as number 1. Okay, so I'm asking, well, what do I multiply by to go from 325 to 108.33 to 36.11? Well, first off, we can say we definitely know that this is going down. These numbers are getting smaller and smaller. So one of the easiest ways to figure out this factor is to take the second term and divide it by the first term. So if we take 108.33, that's really a repeating, and we divide it by 325, we actually would get 0.33 repeating, or as a fraction, it would be 1/3. So we are multiplying every time by 1/3, which is also the same as saying divide every time by 3. So if I'm dividing or multiplying by that fraction, we are getting smaller every time for decay. Okay. Number 3, also we can see that these are getting smaller and smaller. So if we take that same method from number 2, and we're going to take the second value and we're going to divide it by the first value, so 40 divided by 160, we are going to get that this indeed is 1/4, or if you like decimals, we can use 0.25. This b value here is between 0 and 1, so we know that this is a decay. All right, now number 4 here, we're going to go from 2 to 8, 8 to 32. So if we want to keep that same practice in place, we can take this 8 and divide it by the 2, and we're going to see that this b value here is 4. Okay, b values that are greater than 1 tell us we have exponential growth. So what is this going to look like when we put it into a word problem? It says population growth. Suppose 25 flower beetles are left undisturbed in a warehouse bin. The beetle population doubles in size every week. Find the equation using the table. So if we start off at week 0 in this table, what we're going to say is, well, how many beetles did we start with? Well, we started with 25 beetles. And every single week, what's going to happen to those beetles? Their population is going to double in size. So that means if I double 25, we're now at 50. And if we double 50, we're now at 100. And we double that, we're at 200. Double that, we're at 400. And then by week 5, we're at 800 beetles. Okay, so these are like my X's and these are my Y's. Okay, so we can say, well, how did this change? How did I go from 25 to 50 and 50 to 100? Well, we can take that second value, divide it by the first value, and we're going to see that every single time we're going to multiply by 2. Well, doubles means multiply by 2. So y equals our initial value, 25, times our rate here, which is 2, raised to the x power. Now, is this growth or decay? Hopefully we know. It said it was a population growth problem, so that 2 here is telling us that it's greater than 1, so we do know that it's growth. So let's go down here and we're going to graph it over on the left-hand side. So our x's is going to be the weeks. I'm going to label those 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. Okay. And our y-axis is going to be the beetle population. Okay. And on that one, I'm going to label every single one by 25. So 50, 100, 150, 200, 250, 300, 350, 400, 450, oops, sorry, and 500. All right, and when we put this on the graph, I'm just plotting each one of these ordered pairs. So 0, 25, 150, 2, 100, 3, 200, 4, 400, and 5, 800 is off the graph. So I'm going to connect this the best I can. And I'm going to put an arrow going up because it's going to keep going, but no arrow on the left-hand side. So from there we can talk about the domain. Remember, these are our x's from smallest to biggest. Because there's no arrow on the left, we have a bracket from 0 to infinity because of the arrow on the right-hand side. The range is our y's, so 25 is the lowest y value that we have, and the biggest is going to go up forever. All right, on number 6, now we're looking at a decay problem. So this one says, write an exponential function to model a stock losing half of its value every week if the stock was worth $125 starting out. What is it worth after 4 weeks? So we're going to write the equation and then we're actually going to solve for a piece. So let's talk about the values we need. We need to know what A is, we need to know what B is, and then eventually we're going to plug something in for X. So A is our starting value, 125. B is the rate, and here it's a decay. Well, how much is it decreasing? By half every single time. So those two values will help us get our equation. Y equals 125 times 1/2 to the x power. Now we can answer the question, what is it worth after 4 weeks at this rate of decline? So if I plug that 4 weeks in, we're going to use our calculator. We're going to type this in using a 4 in place of that x. And when we do that, we're going to get that y is equal to $7.81. Okay, so we could write a sentence saying that after 4 weeks, this stock will have $7.81 in it. All right, and number 7, we got another one with a graph. So it says, write an exponential function to model the population of mice quadrupling each month if the nest started out with 2 mice. Graph the function. So here we're going to say, well, what is our A value? What are we starting with? We're starting with 2 mice. What's our rate? How is it changing? It's quadrupling each month. Quadruple means 4. Multiplying by 4 every single time. time. And this months part, that's going to tell us our time, which is our x value, how often it's happening. So our equation will be y equals 2 times 4 to the x power. Okay? So let's go ahead and put this on the graph. We've got months down here, that's our x, and we've got the mice population over here. All right, again, I am going to label my x's by 1. I'm only labeling every single other line. And I'm going to label my y-axis by 10s, so every other line will be by 20s. So 20, 40, 60, 80, 100, 120, 140, 160, 180, and 200 at the very top. Okay. So the easiest way is going to be to pull up a table on your calculator and plug in some numbers like 0, 1, 2, 3. Okay. We can go as far as we can. So when we do this, we're going to get 2, 8, 32, 128, 512, and at that point, that's way off my graph. So I'm going to stop there with going just to 4. So let's plot these. So at 0, we're going to be at 2, so that's about here. And 1 is going to be 8, so this middle is 10, so we're going to be below that 10. 2, 32, this is 30, so just above that line. And again, I'm just sketching this the best that I can. 3 is going to be 128, so we're going up to 120, just over halfway up that. And from there I can't go any farther, so I'm going to connect these. And then we can ask ourselves, well, what is f of 24? Well, please remember what function notation tells us. That 24 inside is the x we're going to plug in to the equation. So f of 24 is going to be our equation, which says 2 times 4 raised to the 24th power. Okay, and when we put this in on our calculator, we're going to get a very, very, very large number. Okay, it might not look large because it's going to actually say its number in scientific notation. So it says 5.62950 times 10 to the 14, and this is mice. Okay, I would be happy if you left it in this because this is a really large number. 10 to the 14th means that there are actually 14 zeros if I move this decimal to the right. So I'd have to move it to the right 14 times to get to the large number. That would be how many mice, what the mice population would be at this point. All right, so now what we're going to do is we're going to write a story that could be modeled by this equation. So if you will, take a second, pause it here, try to write it. Okay? Think about what your starting value would be, what your rate, your factor is that you should be changing by, and just give it a little model. All right, so here's the example that I came up with. I bought a gold ring for $150. The value of the ring doubles each year. How much will my ring be worth in 3 years? So you could even then take this problem and say, okay, well, let's solve it in 3 years. So I'm going to plug a 3 in for the x. I would have 150 times 2 to the 3rd power. This would tell me that my ring would be worth $1,200. That would be nice. All right, make sure you got all these notes copied down, and I'll see you tomorrow.